Right, so this is Kirchoff's first law and current, and this is the first section from the Unit 4 from the Electronic Engineering unit. So I'm going to keep this quite brief, and hopefully most of this is just revision from the Science for Engineering stuff. Those of you that do physics will have done this in physics as well, and bits of this are in GCSE. So current then, to start with, so current measured in amps is the rate of flow of charge around a circuit, and in most circuits that involves looking at electrons and counting up how many electrons are passing through a particular point each second. If you did that, if you built an ammeter which counted single electrons and told you that how many electrons are passing through the ammeter every second, you would be measuring current. Only the units would be different, because current isn't actually the number of electrons passing a point each second. It's the amount of electric charge in coulombs that's passing a point each second. So in equation form, it's current in amps is charge in coulombs divided by time in seconds. So if you have a current of 13 amps here, that means that there are 13 coulombs of charge passing a point every second, and each individual electron carries a charge of just 1.6 times 10 to the minus 19 coulombs. So that means that you would have an enormous number of electrons passing through every second. It would be 13 divided by 1.6 times 10 to the minus 19, which I'm just doing on my calculator now, is 8.125 times 10 to the 19 electrons. So an enormous number. So we can't deal with currents or we're counting the individual electrons because there are simply too many. So we lump the electrons together into these groups of charge in coulombs. So that's current. So current is the rate of flow of charge over time. What's much more useful for us in this circuit here, Kirchoff's second idea that you've got 5 amps going in, 2.5 and 2.5 coming out. Some junction, some kind of junction showing the current going in is the same as the current coming out. And question 3 is where there's a bit more to think about with this. So copy and complete the diagrams below stating both the magnitude and the direction of the missing electric currents. So here you've got 10 amps going into this junction, 3 amps going out here, so that's a difference of 7 amps going this way. So A part 1 here, AI, must be 7, and then that 7 amps is being split again at this junction here. You've got 2 amps going that way, so A2, AII, must be 7 take away 2, so it must be 5 amps. For B, you've got 6 amps going in, you've got 10 amps coming out here. That means you must have 4 amps going this way towards that junction. So part 3, BIII, must be 4 amps going towards this junction, so 4 amps going that way. For C, you've got 7 amps going in here to this junction, 9 amps going away from that junction, so it means that part 4 must be 2 amps going towards that junction there, so it'd be 7 plus 2 equals 9. Then 9 amps going this way, going into the junction, so 9 amps going in, 14 amps going out, so it means you must have 5 amps going from right, so this is part 5 here, 5 amps going from right to left into this junction, and then if you've got 5 amps coming this way and 2 amps going that way, then you must have 7 amps coming along here. So part 6 here must be 7 amps going in.